So for this presentation today, we are talking about infrared emissions and Polaron states in these quantum dots, and if we can somehow change anything about them. So a brief explanation, let me just actually minimize this. So a brief explanation of these, what are known about these quantum dots? So a bunch of them, if they become into a cluster, in this case, we have a lead bromide 6, and there's about like 47, 48 in a cluster. They form what is called a nanocrystal. And these nanocrystals are very small, as shown here. Very small crystals. As the electrons enter the nanocrystal will start to produce the light and therefore start to illuminate that crystal. Right now, we know that the larger the space that's inside the crystal, there's going to be a difference in color. So if we can theoretically change the speed of the electron as it enters the crystal, would it have a different effect on the crystal? Would it, more specifically, as the momentum increases, does the temperature increase? Does the nanocrystal enter the Polaron state faster because of its energy potential due to the momentum increasing? And there's also some other things that I recommend at the end of the study that we go ahead and look at and maybe suggest for further research. So here is our wave function. This first dashed line that's right here, this is our ground state, and then this solid line up here is the excited state of the electron. So we're trying to get the electron from its ground state to its excited state. In order to do that, it naturally does it on its own, but if we could somehow get it into that state quicker, or if there's a more efficient speed that we can get that in, that would be the best possible option. Here we are showing this wave packet. This is when the momentum is 18 atomic units. And I'll show you the equations on the next slide. But essentially, this is just doing the nice bounce, bounce, bounce. Again, this is our excited state. This is our ground state, and that also corresponds to here. So this red line right here is our ground state. I'm not sure if you can actually see my pointer. This red state right here is our ground state, and this is our excited state of the electron. So here is the one of two slides where it is mostly equations. This first one right here that I want to preface, this is our Hamiltonian operator, which will go into this Hamiltonian matrix. And you will use the H up and the H down to help formulate as well this matrix, because you plug them into those places within the equation. In the path equation, we also see that we have a V up and a V down. So that is calculated through here. So you have for V up, the big difference between these two is that this is the change in energy with this, whereas this is minus your X down. The big wave packet that we are looking at, and that really comes into play where the change in momentum comes in, is this wave packet, these two. And so our change of momentum is going to be P naught as seen here. So if we could theoretically increase that P naught or decrease it, what would happen? So again, that's how the momentum comes into play. It'll affect the yield versus the time in the atomic units. For this, I chose a series of different momentums, again, within the atomic units, all the way from 0.1 to 20. And as you can see from this slope over here, the slope kind of does like a parabola almost. If we can see here, I feel like we need more data down this side, so that's more data for another time to consider, but then we'd be going into what is the negative momentum, which isn't, which is possible. but it's kind of making this sort of quadratic or parabola shape. So we can see here that this top portion is the ideal momentum for our particle, for our nanocrystal and our electron. As we can also see here, as this P naught increases, we can calculate the temperature. This calculates the temperature into Kelvin. So this equation down here, and that is this conversion on the side is what the conversion is to convert it from the electronic volts to Kelvin. P naught, which is here, we can see that our temperatures are very unrealistic until we get to about here on the table. Otherwise, we're going to be very close to absolute zero, which doesn't happen. We calculate this slope by taking these 2 points here on our graph, which is also equal to our rate. And the rate is really what's important for these columns over here. The inverse temperature, again, it's just 1 over the temperature or Kelvin. We can see, again, it's sort of making this kind of parabola shape. So what does this graph mean? We can see here that this slope is an average negative slope. So that means as the momentum gets larger, theoretically, the activation energy for the electron would get smaller, or the more specifically, the activation energy to get it into the Polaron state would be smaller. And again, like we can see up here, we can see that there is a general range of where it would be prime for it to do it. So it's between 5 and about 12. So what does this mean? This means, as a whole, that we have our hypothesis in the beginning, which is confirmed. Our hypothesis at the beginning was as the rate increases, so if we can increase the rate of the electron going into the nanocrystal, does that get hotter? And the answer is yes. And theoretically, could we also mean that as the momentum increases, we have the rate getting quicker as well? So theoretically, it could mean that that it enters the Polaron state faster. And we can see that also within the data as well. Now, for future research, I do want to. There is a nice area of study where if we can because we can prove that theoretically we can control these electrons as they enter into the crystal. Does the vibrancy of that color increase within that crystal or within that solution because of the momentum? Or would it have some sort of differing effect? Would it have a different color, or would it have a different, any different other properties that we haven't covered here? And thank you so much.